What angle gives the longest trajectory of a thrown ball? So we can think about three questions that will help us answer this. First is, how can we describe the path? Next is, how can we find the length? How can we find the angle at which gives the maximum length? Those are the three questions that will help us answer this problem. So, how is a path described? Let's start with that. Anywhere on Earth, your path will look something like this, or anywhere in a gravitational field. You have an initial velocity v, which has two components. You have a v cos theta component and a v sin theta component. And both of these make up v. How can we describe this path itself? So you can use the kinematic equations and you can combine them to give you a full picture. So if I take this point here, or any point on the path, I can give it an x coordinate and a y coordinate. And I can do this by combining kinematic equations. So basically the equations for constant acceleration. So if I resolve vertically, s equals y, u equals v sine theta, v equals, we don't care, a equals minus g, t equals t, and if I resolve horizontally, s equals x, v equals v cos theta, and t equals t. So the common factor is the t, so we can use time to combine these equations. So if we go up to the top resolved one, use the equation s equals ut plus half at squared, we get v sine theta t minus half gt squared. For across, we get equals x, so this is y, x equals v cos theta t. So to combine these, we can turn this into t equals x over v cos theta, and then put that into here, we get y equals v sine theta times x over v cos theta minus half g times x over all squared now we can make this to x times sine theta over cos theta minus half g times x squared over v squared cos squared theta, and that equals x tan theta minus x squared g over 2v squared cos squared theta. So as you may see, this is just a simple quadratic equation. Well, not really simple, but it is a quadratic equation. Okay, so now we've got an equation for the path. How can we find the length? Here's where this thing called the arc length integral comes in. It looks a bit like this. Well, it does look like this. So what do we mean by this, and what does it exactly do? So it gives the length of a line or a function between 2 points. So if my function looked like this, then what it does, it does Pythagoras, right, on a very small scale, and it sums up these very small distances. So it looks something like this. So that's a small change in x, small change in y, and then that equals to dx squared plus dy squared according to Pythagoras theorem. And then what this integral does is it just sums these tiny little things across the entire curve. Okay, so now you actually have to define 2 points that you want to do it between, obviously, because otherwise you're going to be integrating forever. You're not going to get an answer. So let's take our equation, y equals x tan theta minus x squared g over 2v squared cos squared theta, and set that equal to 0. So now x so we set x equal to 0, then that's one of the solutions. And then we also have tan theta minus x over g 2v squared cos squared theta equals 0. That means tan theta equals that. That means that we do 2v squared tan theta times cos squared theta over g equals x. So tan theta is sin theta over cos theta, so we can cancel out one of the causes, so we get v squared times 2, let me just show you, cancel out one of the causes, and then we should get, so that's one of our bounds, and then the other bound is x equals v squared over g times 2 sine theta cos theta. Okay, so that's going to be our top bound, and this is going to be our bottom bound. Alright, so we now have to find dy by dx. So y again is and dy by dx equals tan theta minus x times g over v squared cos squared theta. So the 2 is actually cancelled out, so because that would be 2 times x. You know what, I might as well just show it. So 2 times the 2 from here, so those 2 cancel, and that's what we're left with. So now what would our integral look like? It look a bit like this. 2 sine theta cos theta 0 1 plus tan theta minus x times g over v squared cos squared theta all squared dx. So what can we do to make it a bit easier? You know what I'll say? You can do this. We can use a substitution. U set that equal to, inside this bracket, dy by dx. first of all we need to isolate dx, get that in terms of u. So du by dx equals minus g over v squared cos squared theta. Now that means that dx equals minus v squared cos squared theta over g times du. Yeah, that's theta, and this again is theta. Okay, so that's dx. Alright, so now we need to get these bounds in terms of the new variable u as well. So if x equals 0, u equals tan theta minus 0 times g over v squared cos squared theta. So u will equal tan theta. Now if x equals v squared over g 2 sine theta cos theta, u will equal tan theta minus v squared over g 2 sine theta cos theta times g over v squared times 1 over cos squared theta. Bear in mind, there's no difference between this and that. I just split it up a little bit to make it a bit more convenient. So what can we do here? These are basically on the same side. We can cancel these out. They're multiplied by each other, don't be clear, but they're multiplied by each other. Here we have a cos squared theta and a cos theta. Cancel those out. Then we got tan theta minus 2 sine theta cos theta. So this is what our integral will look like. We've got minus tan theta on the top. We've got tan theta on the bottom, which is quite confusing, but that's just how these integrals work. Now we got 1 plus u squared times minus v squared cos squared theta over g times du. And now we will do this, bring those out, because effectively this is a constant. Minus v squared cos squared theta over g minus tan theta and tan theta. Okay, so it looks much simpler than before, right? But the thing is, when I have 1 plus u squared, I can't integrate that directly. So again, we're going to have to use a substitution. U equals tan z. Alright? So now figure out the bounds first. So if that's the case, then actually, you know what? Let's start with differentiating it. So du by dz equals sec squared z. So du equals. Okay, now let's also find these bounds in terms of z. So if u equals tan z, then arc tan u, which is basically the same as equals z, right? So if my value of u equals minus tan theta, which is also the same as saying tan of minus theta, if you look at the angles, this is how it works. It's just always like that. That's a rule, yeah? we can do z equals arctan of tan minus theta. Because they're inverse functions, they get rid of each other, and we just get live with minus theta. And then u equals tan theta. That will leave us with theta. Z equals theta. Alright, so now this is what our integral looks like. Still got this constant outside of the integral. We got minus theta here, and we got theta here. Then we got 1 plus tan squared z, because this is u squared, so u equals tan z, square it, you got 1 plus tan squared z, times sec squared z dz. Alright, so that equals minus v squared cos squared theta over g minus theta sec z, because 1 plus tan squared z equals sec squared z, root that, we get sec z times sec squared z dz. Alright, so from here, do a integration by parts. This equals sec cubed z, but we don't really know what the integral of that is, so this will be an easy way to get that out. It's not usually a standard integral for me, so I'm not gonna search up on the internet. I'm just gonna do it like this. So this is how I do integration by parts. We have sec z and sec squared z. This becomes tan z, and this becomes sec z tan z. So this is what our integral by parts will look like. Actually, let's forget all the constants at the moment. We'll just consider the integral sec cubed z dz. Yeah, just forget about the rest of it for the moment. We'll just focus on this. Yeah. So this is the integration by parts. Sec z tan z minus integral of sec squared z, sec z tan squared z dz. So that's sec z tan z minus sec z. So tan squared z equals sec squared z minus 1. Sec z tan z minus. Okay, alright, so we got that integral. Now, first and foremost, what do we do from here? We've ended up with the same thing again and again. Let me rewrite this as sec z tan z minus sec cubed z dz minus, actually wait, this is going to be plus, because we've got this out here. We've got the minus out here, and we've got a minus minus minus, that's going to be plus. Yep, but if we now remember that equals this expression, we can now do this. Sec z tan z plus sec z dz. So our integral of sec cubed z dz equals half sec z tan z plus half sec z dz. Okay, alright, now we can simply integrate this, and what it's going to look like is just this, half sec z tan z equals, we use the plus half, we use the simple standard formula for this, which is ln of sec z plus tan z, and we've integrated it. Now all we need to do is sub in the bounds. Okay, so I've got half sec z tan z plus half ln sec z plus tan z between minus theta and theta, and then here we've got oh yes, I forgot to bring this back in. We've got minus v squared cos squared theta over g. Yep. So let's actually expand this. We'll just remember this, yeah. We'll bring it back in the end. We'll bring it back right at the end. But don't forget this, yeah. We'll just work with the bounds at the moment. So since it's quite big, I'm going to split it into two chunks. So this is going to be upper bound, and let's just simplify that first. So if you know the identities for the odd and even functions, sec minus theta is 1 over cos minus theta. Therefore, we will just keep that as sec theta. Tan minus theta is, again, as I mentioned before, minus tan theta, and vice versa. So the minus sign arises from that. So this is what it looks like. That's the upper bound. Now we've got lower bound, which is literally subbed in. I'm just gonna write out, there's nothing to do here. Okay, so now we gotta do upper minus lower. I'll spare you the trouble, and it just looks like this. Minus sec theta tan theta. So this will be our integral for the moment. Actually, we'll just say upper minus lower, sec theta minus tan theta, and you have plus half ln sec theta minus tan theta divided by sec theta plus tan theta. Okay, now to simplify this, we do minus sec theta tan theta plus half ln 1 over cos theta minus sin theta over cos theta over 1 over cos theta plus sin theta over cos theta. Okay, now that will just equal minus 1 over cos theta times sine theta over cos theta plus half ln 1 minus sine theta over 1 plus sine theta. Now that is the upper bound minus lower bound, and our integral looks like this. We need to bring in the minus v squared cos squared theta over g, and we got the minus sine theta over cos squared theta plus half ln 1 minus sine theta over 1 plus sine theta. And now we just bring in the minus cos squared theta because we want an expression in theta. We got minus v squared over g. On the final integral, it's not supposed to be minus v squared over g, it's supposed to be v squared over g because we brought the minus sign with the cos squared theta into the brackets. If you multiply that by minus cos squared theta, we get sine theta minus half cos squared theta ln 1 minus sine theta or 1 plus sine theta. This is the hardest part. Now it comes to the easy part. Okay, so I'll cut you the long story. Differentiating leads to no solutions in this. Is you just don't get an answer, you can't solve it algebraically. So what we're going to do from here, go on Desmos.com and we're going to graph this. I've plotted the function on Desmos.com and change the settings so that it measures in degrees, change the x-axis so it goes from 0 to 90 degrees, and yeah, put it in, make sure you don't forget the mod sign. And this is the easiest way to find the maximum, and the value that I got was 56.466 degrees, and that will be the angle that gives you the longest trajectory of a thrown ball.